Welcome to Sleeping Researcher, where science narration gently guides you into restful sleep. Here we explore the wonders of the natural world with calm and thoughtful stories designed to soothe your mind and ease you into tranquility. Today we will journey through the vast history of mass extinctions, those rare but profound moments when life on Earth faced great upheaval. These events reshaped the planet's ecosystems and set the stage for new forms of life to emerge. Mass extinctions may sound alarming, but they are also chapters of renewal and transformation. We will explore how life responded after each extinction, slowly recovering and evolving in surprising ways. As we move through time, from ancient oceans to lush forests and sprawling continents, you will discover the delicate balance between destruction and rebirth that has defined Earth's long story. This calm reflection will help you appreciate the resilience of life in a gentle, peaceful way. If this interests you, please take a moment to like this video and subscribe to Sleeping Researcher. Your support helps us continue our work. So, settle in comfortably, breathe deeply, and allow your mind to drift as we begin this serene exploration of mass extinctions and the quiet miracles that follow. Imagine the Earth as a vast, ancient tapestry, woven through eons with the threads of countless species. This tapestry, however, has not been untouched by calamity. Throughout the planet's deep history, life has faced moments of profound upheaval, known as mass extinctions, periods when a significant proportion of all living organisms vanished in relatively short spans of geological time. These events, though catastrophic, serve as critical turning points that have dramatically reshaped the course of evolution. Understanding mass extinctions is not simply an exercise in recounting past tragedies. Rather, it reveals how resilience and renewal have repeatedly emerged from the ashes, guiding the diversity and complexity of life we witness today. Mass extinctions are characterized by a rapid and widespread loss of species across multiple habitats. Scientists have identified 5 major mass extinctions in Earth's history, each marked by unique causes and consequences. The most famous of these, the Permian-Triassic extinction about 252 million years ago, eradicated approximately 90% of marine species and 70% of terrestrial vertebrates. These events often stem from a combination of environmental stresses, volcanic eruptions, climate shifts, asteroid impacts, and ocean chemistry changes that disrupt ecosystems on a global scale. By examining the fossil record and geological clues, researchers piece together the intricate narratives behind these biological crises, offering insight into the fragility and adaptability of life. What follows a mass extinction is as remarkable as the event itself. The aftermath is a time of ecological vacancy, where once dominant species have disappeared, leaving open niches that encourage evolutionary experimentation and diversification. This period of recovery, often spanning millions of years, allows new life forms to rise and ecosystems to rebuild in novel and sometimes unexpected ways. It is through these regenerative phases that the tree of life has been pruned and reshaped, leading to the emergence of new lineages and the great biodiversity we know today. The study of these recovery patterns reveals not only the resilience of life, but also the delicate balance that sustains it. In contemplating mass extinctions, we also gain perspective on the interconnectedness of Earth's biosphere and the profound impact that environmental changes can exert on living systems. Each extinction event underscores the vulnerability of species to rapid shifts in climate, habitat loss, and other stressors. Lessons that resonate deeply with contemporary concerns about biodiversity and conservation. The ancient past thus informs our understanding of present and future challenges, reminding us that the story of life is one of both fragility and enduring hope. This evolving narrative invites us to explore further how life has continuously adapted and transformed through the epochs. To understand the significance of mass extinctions, it is important first to define what they truly entail. Unlike the steady background rate of species loss that occurs naturally over millions of years, a mass extinction is characterized by a relatively rapid and widespread decrease in biodiversity across multiple groups of organisms. Scientists typically recognize a mass extinction when at least 75% of species vanish within a geologically short timeframe, often spanning hundreds of thousands to a few million years. This threshold helps distinguish these extraordinary events from the more gradual ebb and flow of life on Earth. The fossil record serves as our primary window into these moments of crisis, revealing patterns of disappearance and survival that have shaped the evolutionary trajectory of countless lineages. By clarifying what qualifies as a mass extinction, we set the stage for exploring their profound impact on the biosphere, a story marked by devastation, resilience, and renewal. Throughout Earth's history, there have been 5 major mass extinctions, often referred to as the Big Five. These include the Ordovician-Silurian, Late Devonian, Permian-Triassic, Triassic-Jurassic, and Cretaceous-Paleogene events. Each of these episodes involved environmental upheavals such as drastic climate shifts, volcanic eruptions, ocean anoxia, and asteroid impacts. These forces disrupted ecosystems on a global scale and led to the collapse of dominant species groups. For example, the Permian-Triassic extinction, also known as the Great Dying, eradicated an estimated 90 to 95% of marine species and 70% of terrestrial vertebrates, marking the most severe loss of life in Earth's history. Recognizing these patterns allows us to appreciate the scale and intensity of such biological crises, which are far more than isolated incidents. They are pivotal moments that reset the evolutionary playing field. After a mass extinction, the biosphere does not simply return to its previous state. Instead, it enters a prolonged phase of ecological recovery and evolutionary innovation. New niches open up as dominant groups vanish, providing opportunities for survivors and new life forms to diversify and adapt. This process can take millions of years, during which ecosystems gradually regain complexity and stability. The fossil record shows how life has rebounded repeatedly, with new species emerging to fill the void left by those lost. For instance, following the extinction at the end of the Cretaceous period, which famously ended the reign of the non-avian dinosaurs, mammals underwent a significant adaptive radiation, eventually leading to the diverse forms we see today. Thus, Mass extinctions are not only episodes of loss, but also catalysts for transformation, shaping the evolutionary pathways of life on Earth. It is also important to recognize that mass extinctions affect not only individual species, but entire ecosystems and the interactions among organisms. Food webs collapse and reassemble in new configurations. The balance between predators, prey, and producers shifts dramatically. These changes influence the flow of energy and nutrients across the planet, affecting everything from soil composition to atmospheric chemistry. Such profound ecological upheavals demonstrate the interconnectedness of life and environment on a planetary scale. Understanding the mechanisms behind these shifts deepens our appreciation of Earth's dynamic systems and highlights the delicate balance required to sustain biodiversity. This perspective encourages us to consider how current environmental changes might echo past events and influence the future of life. In defining mass extinctions and examining their aftermath, we gain insight into the resilience and vulnerability inherent in life's history. These events remind us that extinction is a natural, albeit dramatic part of the evolutionary process. Yet, they also challenge us to reflect on the factors that drive such losses and the ways in which life adapts and thrives anew. As we continue this exploration, we will delve deeper into specific mass extinction events and the remarkable stories of survival and recovery that followed. This ongoing journey through Earth's past invites us to see the ever-changing tapestry of life with renewed understanding and reverence. Throughout Earth's deep history, life has faced numerous challenges, but none as profound as the 5 major mass extinction events, often referred to as the Big Five. These pivotal moments, spread across hundreds of millions of years, mark times when vast numbers of species vanished from the planet in relatively short geological periods. By studying these 5 extinction events, the Ordovician Silurian, Late Devonian, Permian Triassic, Triassic Jurassic, and the Cretaceous Paleogene, we uncover patterns that reveal both the fragility and resilience of life. Each extinction brought a dramatic reshaping of ecosystems, wiping out dominant groups and paving the way for new forms of life to evolve and flourish. These episodes are not merely tragic losses, they are critical junctures in Earth's biological narrative, offering windows into how life responds to extreme environmental stress and how biodiversity rebounds over time. The earliest of these, the Ordovician Silurian extinction, occurred roughly 445 million years ago and was likely triggered by a rapid ice age that drastically altered sea levels and habitats. Life in the oceans, which dominated the planet at the time, suffered greatly, with many marine species disappearing. This event was followed by the Late Devonian extinction, about 375 million years ago, another prolonged crisis that targeted primarily marine life. Both extinctions underscore a recurring theme. Changes in climate and ocean chemistry can disrupt ecosystems on a massive scale. Yet, after these losses, life slowly adapted, eventually leading to the rise of new species and ecosystems, illustrating nature's remarkable capacity for recovery. Perhaps the most devastating of all was the Permian-Triassic extinction, approximately 252 million years ago, often called the Great Dying. This event erased nearly 90% of marine species and a significant proportion of terrestrial life, reshaping the course of evolution. The causes are complex, likely involving massive volcanic eruptions, climate shifts, and ocean anoxia. The aftermath was a world transformed, but from this devastation emerged new groups, such as the early dinosaurs and mammals, which would come to dominate in the following eras. This profound turnover highlights how mass extinctions, while catastrophic, also act as catalysts for evolutionary innovation and diversification. The Triassic-Jurassic extinction, around 201 million years ago, though less severe, cleared the way for the dominance of dinosaurs, while the most recent of the Big Five, the Cretaceous-Paleogene extinction 66 million years ago, famously ended the reign of the non-avian dinosaurs. This last event, caused by an asteroid impact and volcanic activity, reshaped Earth's ecosystems dramatically, allowing mammals to rise and eventually give birth to the biodiversity we see today. Each extinction event serves as a reminder of the dynamic interplay between environmental change and life's evolutionary pathways. By studying these periods, scientists can better understand the mechanisms behind extinction and recovery, informing our perspective on current and future biodiversity challenges. Observing the patterns woven through these 5 major extinctions reveals cycles of collapse and renewal, where life's diversity is both diminished and reborn. After each event, ecosystems reorganize, species radiate into new niches, and evolutionary innovation accelerates. This pattern of devastation followed by recovery teaches us about the resilience inherent in life on Earth and the delicate balance that sustains it. As we continue to explore these remarkable transitions, we gain deeper appreciation for the complexities of survival and adaptation in the face of profound change. Among the earliest of Earth's great biological crises, the end-Ordovician extinction stands as a profound example of how shifts in climate can ripple through the delicate web of life. Occurring approximately 445 million years ago, this event saw the loss of nearly 85% of marine species, a staggering toll given that life was predominantly oceanic at the time. The driving forces behind this extinction are closely tied to dramatic changes in the planet's climate, notably a severe glaciation that drew down sea levels and transformed habitats. As vast ice sheets formed on the ancient supercontinent Gondwana, shallow seas, home to diverse marine communities, receded, fragmenting ecosystems and forcing species into increasingly isolated refuges. This environmental upheaval disrupted food chains and reproductive cycles, making survival an immense challenge for many organisms. The scale of extinction underscores the vulnerability of life to rapid and sustained climate shifts, reminding us that even in deep time, Earth's environmental balance has been fragile and dynamic. The aftermath of the End-Ordovician extinction reveals the resilience and adaptability woven into the fabric of life's history. Following this period of loss, surviving species found new opportunities to diversify and expand into niches left vacant by their extinct predecessors. This adaptive radiation fostered evolutionary innovation, setting the stage for the Ordovician's Silurian transition and the flourishing of new marine forms. Coral reefs, brachiopods, and early jawless fish, among others, began to repopulate the seas, each group exploring ecological roles with fresh vigor. These evolutionary responses highlight the intricate interplay between extinction and emergence. How the cessation of one chapter in life's story often signals the beginning of another. Ecosystems gradually reassembled, demonstrating a remarkable capacity to reorganize despite profound disturbance. The End-Ordovician event thus offers a window into the cyclical dance of destruction and renewal that has characterized Earth's biological past. Studying this extinction also reveals valuable lessons about the interconnectedness of climate, geology, and biology. The glaciation that precipitated the End-Ordovician crisis was linked to shifts in atmospheric carbon dioxide, continental positioning, and ocean chemistry. These factors combine to create inhospitable conditions for many marine species, emphasizing how changes in one sphere of the Earth system can cascade across others. In modern times, as we observe rapid climate change once again altering habitats and species distributions, the End-Ordovician extinction serves as a poignant reminder of nature's sensitivity to environmental stress. Understanding this ancient event enriches our perspective on the challenges faced by contemporary ecosystems and the potential consequences of ongoing climate shifts. The fossil record becomes a narrative of caution and hope, illustrating both the risks of instability and the enduring strength of life to adapt. Beyond the immediate biological impacts, the End-Ordovician extinction influenced the trajectory of Earth's evolutionary history in subtle yet profound ways. By reshaping marine communities, it altered food webs and ecological interactions, laying groundwork for the Silurian period's diversification. The extinction also affected sedimentation patterns and geochemical cycles, linking biology and geology in a continuous dialogue. As species recovered, evolutionary experimentation accelerated, eventually contributing to the rise of more complex organisms and ecosystems. This intricate process of recovery and change invites reflection on the deep timescales over which life evolves, reminding us that extinction events are not merely endings, but also beginnings filled with potential. Through this lens, we come to appreciate the delicate balance of forces that govern life's persistence on our planet. As we consider the End-Ordovician extinction in the broader context of Earth's history, its lessons extend naturally toward understanding later mass extinctions and the varied patterns they embody. Each event carries unique causes and consequences, yet all share threads of climate influence, ecological disruption, and evolutionary renewal. Moving forward, we shall explore another profound mass extinction, the late Devonian event, where the story of life's resilience continues to unfold, marked by equally dramatic shifts and remarkable recoveries. This ongoing journey through Earth's deep past enriches our appreciation for the dynamic interplay of life and environment. A narrative as endless as it is enlightening. The late Devonian extinction, occurring approximately 375 million years ago, stands as one of the most prolonged and intricate extinction events in Earth's deep history. Unlike some mass extinctions characterized by rapid and catastrophic losses, this event unfolded over millions of years, marked by a series of pulses rather than a singular sudden crisis. It primarily affected marine environments, where reef-building organisms, such as stromatoporoids and corals, experienced dramatic declines. These reefs had thrived for millions of years and formed complex habitats that supported diverse marine life. The gradual but persistent disappearance of these foundational species led to profound shifts in ocean ecosystems. Scientists believe that factors such as widespread anoxia, oxygen depletion in ocean waters, along with climate fluctuations and possibly changes in sea levels, contributed to this extended crisis. This extinction event, therefore, illustrates the complexity of extinction processes, where multiple environmental stresses can interplay over long timescales, gradually pushing ecosystems toward collapse rather than abrupt devastation. The aftermath of the late Devonian extinction reveals a fascinating narrative of ecological transformation and evolutionary innovation. As the dominant reef builders and many marine species declined, new groups found opportunities to diversify and fill the ecological vacancies left behind. Early jawed fishes, including the ancestors of modern sharks and bony fishes, began to rise in prominence, shaping future aquatic food webs. On the seabed, the decline of reefs allowed for the expansion of soft-bodied organisms and different types of microbial mats, which altered sediment dynamics and nutrient cycling. This gradual reorganization of marine communities underscores an important aspect of mass extinctions. They are not mere endpoints, but also starting points for new evolutionary chapters. The shifting balance of life during and after the late Devonian event highlights how resilience and adaptability are woven into the fabric of Earth's biosphere, responding to adversity with innovation and diversification. Intriguingly, the late Devonian extinction also coincides with significant changes on land, where early terrestrial ecosystems were beginning to take shape. The Devonian period saw the emergence of the first extensive forests, composed largely of primitive vascular plants. These early trees contributed to soil formation and influenced atmospheric composition by drawing down carbon dioxide. Some scientists suggest that the expansion of these forests may have played a role in the extinction event itself, through complex feedbacks involving climate cooling and changes in ocean chemistry. The interplay between terrestrial and marine realms during this time reminds us that Earth's systems are deeply interconnected, with life on land and sea influencing one another in profound ways. Such insights deepen our understanding of how environmental change can ripple across the planet, affecting ecosystems in multiple dimensions and across vast timescales. The late Devonian extinction, with its drawn-out duration and multifaceted causes, challenges simple narratives about mass extinctions as sudden catastrophes. Instead, it invites us to consider how environmental pressures accumulate and interact, to reshape life over extended periods. This event exemplifies a pattern that recurs throughout Earth's history, where extinction and recovery are entwined in an ongoing dance, each phase setting the stage for the next. As ecosystems falter and species vanish, new opportunities arise for survivors to adapt and radiate into the vacated niches. Such complexity enriches our perspective on the resilience of life and the dynamic nature of planetary change. Understanding these processes encourages a thoughtful appreciation of the delicate balances that sustain biodiversity, even amid profound transformations. As we reflect on the late Devonian extinction and its enduring impact on marine and terrestrial life, we prepare to explore yet another pivotal chapter in Earth's history. The narrative of mass extinctions continues to unfold, revealing further episodes where climate change, geological upheaval, and biological responses converge in shaping the destiny of life. Ahead lies the story of the Permian-Triassic extinction, often called the Great Dying, which presents a dramatic contrast in scale and immediacy. In contemplating these successive events, we deepen our understanding of the myriad ways Earth's biosphere has been challenged and renewed, a testament to both fragility and persistence. As we turn our attention to the close of the Permian period, roughly 252 million years ago, we encounter an event unparalleled in the annals of Earth's history. Known as the End Permian Extinction, or the Great Dying, this catastrophic episode eradicated an estimated 90 to 96% of all marine species and around 70% of terrestrial vertebrate species. The scale of this loss is staggering. Vast ecosystems that had flourished for millions of years were abruptly dismantled. Scientists have pieced together evidence pointing to massive volcanic eruptions in what is now Siberia as a primary driver. These eruptions released enormous volumes of greenhouse gases, including carbon dioxide and methane, triggering drastic climate shifts. Ocean temperatures soared, oxygen levels plummeted, and acidification disrupted marine habitats. This combination of volcanic fury and rapid climate change overwhelmed life on Earth in ways previously unseen. The volcanic activity responsible for the Great Dying is linked to what is known as the Siberian Traps, a vast region of basaltic lava flows covering millions of square kilometers. The sustained eruptions released not only heat but also toxic gases that permeated the atmosphere and oceans. As global temperatures rose, delicate balances in ecosystems were shattered. Methane clathrates trapped in ocean sediments may have been destabilized, releasing further greenhouse gases and amplifying warming in a feedback loop. The oceans became inhospitable, suffering from widespread anoxia, zones deprived of oxygen, and acidification, which undermined the shells and skeletons of many marine organisms. On land, ecosystems faced drought, soil erosion, and the collapse of food chains. Over time, the biosphere was pushed to a tipping point where survival became a monumental challenge for most life forms. In the aftermath of the Great Dying, Earth was a profoundly altered world. The extinction event cleared vast ecological niches, setting the stage for evolutionary experimentation and diversification. Though life was nearly extinguished, it also found ways to adapt and eventually thrive. The early Triassic period that followed was marked by a slow but steady recovery, beginning with opportunistic species that could tolerate harsh conditions. Reefs, which had been decimated, gradually reappeared, and new groups of plants and animals began to emerge. This recovery was neither quick nor straightforward. It took millions of years for ecosystems to regain complexity comparable to those lost. Yet, this slow renewal underscores the resilience of life, demonstrating how mass extinctions, while devastating, can also serve as catalysts for evolutionary change. The profound lessons of the end Permian extinction extend beyond its ancient context, offering insights into the interplay between volcanic activity, climate systems, and biological resilience. It serves as a sobering reminder of how rapid environmental changes can cascade into global crises when thresholds are crossed. Modern scientists study this event not only to understand Earth's past, but also to gain perspective on present-day challenges such as anthropogenic climate change and biodiversity loss. The Great Dying reveals the fragile balance that sustains life, and how quickly that balance can be disturbed by natural forces. As we contemplate this cataclysmic chapter, we prepare to explore subsequent mass extinctions, each with its own story of loss and renewal, further illuminating the dynamic history of life on our ever-changing planet. The Permian extinction, often referred to as the Great Dying, was triggered by a complex interplay of geological and atmospheric events, chief among them massive volcanic eruptions. These eruptions originated from the Siberian Traps, an enormous region of volcanic rock that formed over hundreds of thousands of years. The scale of these eruptions was unprecedented, releasing vast quantities of lava, ash, and gases into the atmosphere. Sulfur dioxide and carbon dioxide emissions from the volcanic activity led to severe atmospheric changes, including acid rain and a sharp increase in greenhouse gases. This combination drastically altered the climate, causing global temperatures to soar and disrupting ecosystems on land and in the oceans. The prolonged volcanic activity thus set the stage for a catastrophic environmental collapse, pushing Earth's biosphere beyond its capacity to adapt. In addition to volcanic emissions, one of the most consequential factors behind the Permian extinction was the release of methane from oceanic reservoirs. As warming oceans destabilized methane clathrates, ice-like compounds that trap methane beneath the seafloor, vast amounts of this potent greenhouse gas entered the atmosphere. Methane's presence accelerated global warming further, intensifying ocean stratification and reducing oxygen levels in marine environments. This process, known as ocean anoxia, created vast dead zones where marine life could no longer survive. The interplay between volcanic activity and methane release thus created a feedback loop, amplifying environmental stressors and deepening the ecological crisis. Such cascading effects highlight how interconnected Earth's systems are, and how disturbances in one domain can ripple outward, affecting the entire planet. The The chain reaction set off by these geological events did not only affect the physical environment, but also had profound biological consequences. Terrestrial and marine species alike faced habitat loss, toxic conditions, and severe climate fluctuations. Many ecosystems collapsed as food chains were disrupted, leading to the extinction of approximately 90% of marine species and 70% of terrestrial vertebrate species. The loss of biodiversity was staggering, yet it also paved the way for evolutionary renewal. In the aftermath, new groups of organisms eventually emerged, adapting to the altered conditions and filling ecological niches left vacant. This cycle of destruction and rebirth is a recurring theme in Earth's history, underscoring both the vulnerability and resilience of life. Understanding the causes behind the Permian extinction deepens our appreciation of Earth's delicate balance and the potential consequences when natural systems are pushed beyond their limits. The event illustrates how interconnected geological processes, such as volcanism and methane release, can combine to create environmental tipping points. Modern scientific investigations continue to unravel these mechanisms through the study of rock records, isotopic analyses, and climate modeling. Insights gained from this ancient crisis inform contemporary concerns about greenhouse gas emissions, ocean health, and the long-term stability of ecosystems. As we move forward, it becomes clear that the lessons from the Permian extinction remain relevant, offering a window into the fragility and complexity of the biosphere. As we leave behind the story of the Permian extinction, we turn toward the narratives of other great mass extinctions, each marked by distinct causes and consequences. From the asteroid impact that shaped the fate of the dinosaurs, to the slower, more gradual environmental shifts of other eras, these events reveal diverse pathways to global collapse and recovery. Exploring these episodes further enriches our understanding of Earth's dynamic history and the remarkable adaptability of life. With this in mind, we prepare to delve into the next chapter, examining the forces that drove subsequent mass extinctions and the echoes they leave in the present day. As we turn our attention to the end Triassic extinction, we find ourselves approximately 201 million years in the past, at the boundary between the Triassic and Jurassic periods. This event, though less famous than some others, was one of the major mass extinctions in Earth's history, extinguishing roughly 80% of marine and terrestrial species. Its causes are still the subject of scientific study, but many researchers point to intense volcanic activity associated with the breakup of the supercontinent Pangaea. The massive eruptions of the Central Atlantic magmatic province released vast quantities of carbon dioxide and other gases into the atmosphere, triggering rapid climate warming and ocean acidification. These environmental stresses created inhospitable conditions for many life forms, particularly those heavily reliant on stable marine ecosystems. The result was a profound reshaping of biodiversity, wiping out numerous groups of amphibians, reptiles, and marine organisms that had thrived during the Triassic. Yet, within this great biological upheaval are the seeds of new possibilities. The end Triassic extinction cleared ecological niches that had been dominated by earlier reptilian lineages, opening the door for the rise of the dinosaurs. In the wake of extinction, ecosystems became more flexible and receptive to novel evolutionary experiments. Dinosaurs, which had already appeared during the Triassic, now found reduced competition and an abundance of available habitats. Their adaptability, combined with favorable environmental conditions, allowed them to diversify and occupy a variety of ecological roles. This period marked the dawn of the Mesozoic era, as the age of dinosaurs, the time when these creatures would come to dominate terrestrial ecosystems for over 150 million years. Such transitions reveal how mass extinctions, while devastating, act as powerful agents of change, resetting the biological stage and enabling new chapters in life's story. The aftermath of the end Triassic extinction also illustrates the complex interplay between extinction, recovery, and evolution. Following the initial collapse, ecosystems did not return to their previous states, but instead followed new trajectories shaped by the survivors and the changing environment. Marine ecosystems gradually recovered, with new groups of corals and mollusks establishing themselves over millions of years. On land, the rise of gymnosperms, or seed plants, helped stabilize terrestrial habitats and provided resources for emerging herbivorous dinosaurs. The recovery was neither swift nor uniform. It spanned millions of years and involved numerous ecological adjustments. This slow but steady resurgence highlights the resilience of life and the intricate processes of adaptation and diversification that follow even the most profound crises. Through this lens, we begin to appreciate the enduring cycles of destruction and renewal that have sculpted the history of life on Earth. In reflecting on the end Triassic extinction, we recognize the event as a pivotal moment in Earth's history, a bridge between eras defined by vastly different dominant life forms. It underscores the idea that extinction is not merely an end, but also a transformation, a resetting of ecological balances that can lead to evolutionary innovation. The dominance of dinosaurs in the Jurassic and Cretaceous periods owes much to the opportunities created in this wake of loss. Their eventual success in terrestrial realms reshaped ecosystems, influencing the course of evolution for millions of years to come. This event, like others before and after it, invites us to consider the delicate equilibrium of life and the profound ways in which planetary changes ripple through biological communities. As we turn our attention to the end Cretaceous extinction, we find one of the most dramatic turning points in Earth's biological history. Approximately 66 million years ago, this event abruptly ended the reign of the dinosaurs, creatures that had dominated terrestrial ecosystems for over 150 million years. What sets this extinction apart is its suddenness and the scale of devastation, widely attributed to the impact of a massive asteroid striking the Yucatan Peninsula. forming what is now known as the Chicxulub crater. This colossal collision released an unimaginable amount of energy, triggering a cascade of environmental catastrophes, intense wildfires, tsunamis, and a nuclear winter effect caused by dust and aerosols blocking sunlight. The resulting collapse of food chains led to the extinction of nearly 75% of Earth's species, including all non-avian dinosaurs. This event underscores the profound influence that extraterrestrial forces can have on life on our planet, reminding us that Earth's history is shaped not only by internal geological and biological processes, but also by cosmic events that can abruptly change the trajectory of evolution. In the immediate aftermath of the asteroid impact, the Earth was a drastically altered world. The skies darkened, temperatures plummeted, and photosynthesis slowed, disrupting ecosystems globally. Yet, from this devastation emerged new opportunities for life to adapt and diversify. Mammals, which had existed in the shadow of dinosaurs, found ecological niches suddenly vacated, allowing them to flourish and evolve into the diverse array of forms we see today. Similarly, many plant groups and other animal lineages underwent rapid evolutionary changes in response to the new environmental conditions. This pattern of extinction followed by adaptive radiation illustrates a recurring theme in Earth's history. Periods of mass extinction, while catastrophic, often act as catalysts for evolutionary innovation and the reorganization of life on a planetary scale. It is a humbling reminder of nature's resilience and the dynamic interplay between extinction and emergence. The end Cretaceous extinction also invites reflection on the delicate balance of Earth's systems. The event was not only a biological crisis, but also a geological and climatic upheaval. Volcanic activity, particularly the Deccan Traps in what is now India, may have compounded environmental stresses through prolonged greenhouse gas emissions, adding complexity to the extinction narrative. These overlapping factors highlight how extinction events often result from a confluence of causes, both terrestrial and extraterrestrial. Understanding these multifaceted drivers is crucial as we study past extinctions to better comprehend the vulnerabilities and resilience of life. It also encourages us to appreciate the interconnectedness of Earth's biosphere, atmosphere, and geosphere, each influencing the others across vast spans of time. Such insights deepen our awareness of the forces that shape the living world and the potential consequences when these forces are disrupted. As the dust settled after the end Cretaceous event, the stage was set for the rise of new dominant groups. Birds, the only surviving lineage of dinosaurs, continued to diversify, while mammals began their ascent to ecological prominence. This transition marked the beginning of the Cenozoic era, often called the Age of Mammals, where evolutionary trajectories shifted dramatically. Fossil records reveal how life rebounded, filling ecological vacancies and exploring new adaptive strategies. These patterns emphasize that extinction, while a definitive end for many species, can also be a doorway to renewal and diversification. Such cycles have punctuated Earth's history, each mass extinction followed by a period of recovery and innovation that reshapes the living world in profound ways. We observe in these cycles a testament to life's enduring capacity for change and resilience. Reflecting on the end Cretaceous extinction within the broader context of mass extinctions encourages us to consider the ongoing evolution of Earth's biosphere, the patterns of loss and renewal, driven by forces both within and beyond our planet, offer insights into the fragility and adaptability of life. As we explore subsequent chapters in Earth's history, we will see how similar themes recur, how extinction events serve as both endings and beginnings, continually reshaping the tapestry of life. These events, etched in the geological record, remind us of the dynamic and ever-changing nature of the world we inhabit. With this perspective, we move forward to examine other significant extinction events and their enduring impacts on the story of life. The story of Earth's most famous mass extinction gained remarkable clarity, with the discovery of a thin layer of sediment enriched in iridium, a rare metal on Earth but common in asteroids and comets. This layer, found at the Cretaceous-Paleogene boundary, appeared across the globe, serving as a subtle yet powerful marker of a catastrophic event. The presence of iridium suggested a sudden extraterrestrial source, hinting at an asteroid impact as the trigger for the widespread extinction that affected dinosaurs and many other species. This geochemical fingerprint opened new pathways for understanding how external forces could abruptly reshape life on Earth. As scientists pieced together this evidence, it became clear that the iridium anomaly was more than a curious coincidence. It was a signpost pointing to a moment when the planet's delicate balance was profoundly disturbed. The search for the impact site led to one of the most significant geological discoveries of the 20th century, the Chicxulub crater, buried beneath the Yucatan Peninsula in Mexico. Spanning nearly 150 kilometers in diameter, this massive crater bore the unmistakable hallmarks of a colossal collision. Its size and age corresponded precisely with the timing of the end Cretaceous extinction, strengthening the connection between the impact and the global biological crisis. Drilling into the crater revealed shocked quartz and other impact-related minerals, confirming the violent nature of the event. These findings transformed the asteroid impact hypothesis from a speculative idea to a well-supported scientific explanation for one of Earth's most dramatic extinction episodes. Beyond the physical evidence of the crater and iridium layer, the impact's aftermath is recorded in a global layer of soot and ash, indicating massive wildfires and atmospheric upheaval. The collision would have unleashed a cascade of environmental effects, a cloud of dust and aerosols blocking sunlight, a significant drop in temperatures, and acid rain altering ecosystems worldwide. These rapid changes disrupted food chains and habitats, leading to the collapse of numerous species. Yet, this devastation also paved the way for new life forms to emerge, illustrating the paradox of extinction as a catalyst for evolutionary innovation. The geological and chemical traces together paint a vivid picture of a world transformed in geologic moments, a reminder of both vulnerability and resilience. The integration of multiple lines of evidence, from iridium anomalies to crater geology and fossil records, has made the asteroid impact hypothesis a cornerstone in our understanding of mass extinctions. It underscores the importance of interdisciplinary research, where geology, chemistry, and paleontology converge to unravel Earth's deep history. This approach continues to inspire new discoveries about other extinction events, each with its unique causes and consequences. As we reflect on the Chicxulub impact, we gain perspective on how external cosmic forces can intersect with terrestrial processes to reshape the biosphere in profound ways. Such insights deepen our appreciation of Earth's complex systems and the delicate interplay that sustains life. With the compelling evidence of the Chicxulub crater and iridium layer illuminating the asteroid's role, we are reminded that mass extinctions are not only moments of loss, but also opportunities for renewal. The aftermath of the end Cretaceous event saw the rise of mammals and the eventual flourishing of diverse ecosystems, setting the stage for the world as we know it today. As we continue our exploration into the history of mass extinctions, we will encounter other dramatic events, each revealing new facets of Earth's evolving story. Let us now turn our attention to these other episodes and the lessons they hold about life's persistent journey through change. While the grand narratives of Earth's history often highlight the catastrophic mass extinctions, the ones that erased vast numbers of species in relatively brief geological moments, it is important to recognize that smaller extinction events have also played crucial roles in shaping biodiversity. These more moderate episodes, sometimes called background extinctions, occur over longer spans or with less dramatic intensity. Yet their cumulative effects are profound. Rather than wiping out entire groups, they may selectively prune species, creating ecological vacancies and opportunities for evolutionary innovation. In this way, smaller extinctions act as subtle but persistent forces, guiding the ebb and flow of life's complexity on our planet. Through these events, ecosystems are continuously reshaped, revealing the dynamic interplay between extinction and diversification that underlies the resilience of life itself. Consider, for instance, the repeated regional extinction events that punctuated the Mesozoic and Cenozoic eras. These episodes, often linked to shifts in climate, sea levels, or volcanic activity, did not cause the wholesale devastation of the great mass extinctions, but they nonetheless altered the composition of biological communities. By removing certain species, these smaller extinctions opened niches that other organisms could exploit, fostering adaptive radiations and new ecological relationships. Such changes emphasize that extinction is not merely an ending, but also a process that continually molds the tree of life. The delicate balance between species loss and emergence in these intervals reflects a natural rhythm, one that sustains evolutionary momentum even in the absence of dramatic catastrophes. Observing these patterns deepens our appreciation of how life remains ever responsive to the subtle shifts in Earth's environment. Moreover, these smaller events often serve as natural experiments in resilience, testing the ability of ecosystems and species to adapt to changing conditions. Unlike the sudden shocks of major extinctions, gradual declines or localized die-offs allow for more nuanced responses, such as migration, adaptation, or shifts in reproductive strategies. This incremental pressure can promote genetic diversity and innovation, setting the stage for future evolutionary breakthroughs. In this sense, smaller extinction events contribute to the ongoing refinement of life's tapestry, ensuring that ecosystems do not become static, but remain vibrant and capable of transformation. Their subtle influence is a reminder that extinction is not only about loss, but also about the continuous shaping of life's potential. Recognizing this interplay invites us to look beyond the headlines of planetary crises and appreciate the quieter, persistent forces at work. It is also worth noting that the fossil record reveals a fascinating mosaic of extinction intensities, where small and moderate events often precede or follow the larger catastrophes. These sequences suggest that mass extinctions are not isolated blips, but part of a broader continuum of ecological stress and recovery. Each smaller extinction carries its own signature, sometimes as a prelude hinting at an impending crisis, or as a recovery phase that stabilizes ecosystems after upheaval. This layered history of extinction underscores the complexity of Earth's biosphere and the myriad factors influencing its trajectory. By studying these smaller events, scientists gain valuable insights into the mechanisms of extinction and survival that operate across multiple scales of time and space. Such understanding enriches our perspective on how life endures and transforms through persistent change. As we reflect on the significance of these smaller extinction events, we see that they contribute essential chapters to the grand saga of life on Earth. Their influence on biodiversity reminds us that extinction is neither solely a narrative of devastation nor a rare anomaly, but a fundamental aspect of life's ongoing evolution. The subtle shifts they catalyze help maintain ecological balance and open pathways for new forms of life to emerge and flourish. With this appreciation, we prepare to explore the diverse aftermaths of extinction, how ecosystems recover, reorganize, and blossom in response to loss and transformation. Let us now delve deeper into the processes that follow extinction events and the remarkable stories they tell about life's enduring resilience. When we observe the vast tapestry of Earth's history, patterns begin to emerge in the causes behind mass extinctions. Though each event is unique in its timing and scale, common threads weave through many of these biological crises. Prominently, shifts in climate have repeatedly played a central role. Whether gradual cooling or abrupt warming, these changes disrupt the delicate balance of ecosystems, altering habitats and food availability in profound ways. Alongside climate fluctuations, intense episodes of volcanism have frequently coincided with extinction events. Vast volcanic eruptions release enormous quantities of gases and particulates into the atmosphere, triggering acid rain, blocking sunlight, and ultimately destabilizing the environment. Meanwhile, the dramatic arrival of asteroid or comet impacts has punctuated Earth's story with sudden, catastrophic disruption. The energy unleashed by these collisions can instantaneously reshape landscapes and atmospheres, causing widespread destruction and long-term ecological consequences. By identifying these recurring drivers, climate change, volcanism, and extraterrestrial impacts, we begin to understand the multifaceted triggers that tip life toward extinction. The interplay between these causes often compounds their effects, creating cascading crises that challenge survival on a global scale. For instance, volcanic activity may inject greenhouse gases into the atmosphere, amplifying warming trends already underway. Similarly, an asteroid impact can ignite wildfires and provoke volcanic eruptions, setting off a chain reaction of environmental stresses. These overlapping influences illustrate that mass extinctions seldom arise from a single cause alone. Instead, they reflect complex interactions within Earth's systems, where one disturbance magnifies another. This understanding highlights the intricate connectivity between the geosphere, atmosphere, and biosphere. It also reminds us that life's vulnerability emerges not merely from isolated events, but from the dynamic interplay of multiple forces shaping the planet's destiny. As we consider these patterns, we gain insight into the delicate thresholds that, when crossed, can unravel even the most resilient ecosystems. In recognizing the patterns behind extinction triggers, scientists are better equipped to interpret the fossil record and the clues embedded within ancient sediments. Geochemical signatures, for example, reveal sudden shifts in carbon cycles tied to volcanic emissions or the fallout from asteroid impacts. Likewise, fossil assemblages show abrupt losses of species, marking the passage of these tumultuous times. Through careful analysis, researchers reconstruct the timing and sequence of events, piecing together how life responded to these environmental upheavals. These reconstructions not only deepen our appreciation for the complexity of past extinctions, but also inform present-day efforts to anticipate how current and future changes might affect biodiversity. Understanding these ancient triggers allows us to frame modern challenges within a broader context of Earth's enduring rhythms. Beyond the immediate causes, the aftermath of mass extinctions invites reflection on the resilience and adaptability of life. After the devastating loss of species, ecosystems undergo profound transformation, with survivors adapting to new conditions and niches opening for evolutionary innovation. The patterns we observe in extinction causes thus resonate with the equally important patterns found in recovery. Recognizing these connections encourages a holistic perspective, one that sees extinction not only as an end, but also as a beginning, shaped by the same forces that bring it about. This ongoing dialogue between destruction and renewal continues to sculpt the ever-changing mosaic of life on Earth. As we continue our exploration, it becomes clear that the causes of mass extinction are intertwined with the stories told by the aftermath. How life re-emerges, reorganizes, and flourishes anew. The triggers of extinction set the stage for transformation, guiding the evolutionary pathways that follow. With a deeper understanding of these causes, we are invited to observe the remarkable resilience that defines life's journey, and to anticipate the ways ecosystems respond to profound change. Let us now turn our attention to the processes of recovery and renewal, tracing how Earth's biosphere rebuilds itself after the profound trials of extinction. When mass extinctions occur, the immediate image that comes to mind is one of loss. Vast numbers of species disappearing from the planet's tapestry of life. Yet beyond this profound reduction lies a subtle yet powerful ecological reset. These events, though devastating, act as a kind of blank slate for Earth's ecosystems, clearing away dominant species and opening niches that had long been occupied. In the wake of such upheaval, the survivors and the newly emerging forms of life begin to explore these vacant spaces, setting in motion an evolutionary dance that reshapes biological communities. This process unfolds gradually, often over millions of years, as ecosystems reorganize and diversify. The vacuum created by extinction invites novel adaptations, allowing life to experiment with new strategies for survival and growth. Here, extinction is not merely an end, but a catalyst for renewal, prompting a cascade of ecological and evolutionary changes that redefine the very fabric of living systems. It is fascinating to observe how mass extinctions alter food webs and ecological relationships. When dominant predators or herbivores vanish, the balance of ecosystems shifts dramatically. This restructuring can lead to the proliferation of previously rare species or the emergence of entirely new groups that seize opportunities to thrive. For instance, after the Permian extinction, the largest in Earth's history, ecosystems gradually gave rise to the ancestors of modern reptiles and mammals, setting the stage for the rich diversity we recognize today. The aftermath of extinction is a period marked by both vulnerability and potential. Fragile ecosystems take time to stabilize, yet within that uncertainty lies the chance for evolutionary innovation. These moments of transformation remind us that life is not static. It continually adapts, responding to the constraints and possibilities carved out by extinction events. Recovery following mass extinction is often uneven, unfolding in pulses rather than a smooth continuum. Some species rebound quickly, while others take millions of years to establish themselves fully. This staggered revival reflects the complexity of ecological interactions in the myriad factors influencing survival and adaptation. Environmental conditions such as climate and habitat availability play critical roles in shaping the trajectory of renewal. Over time, new ecosystems emerge, often with different compositions and structures than those that existed before the extinction. This dynamic process highlights the resilience inherent in life's web, in the creative power of evolution to fill the voids left behind. Each recovery phase lays the foundation for future biological innovations, weaving a narrative of continuity amid change. In examining the fossil record, we see countless examples where extinction and subsequent recovery have driven the rise of novel ecosystems. Coral reefs, forests, and grasslands as we know them today all bear the marks of these ancient resets. These new ecosystems do not simply replicate what was lost. Instead, they often represent entirely new configurations of species and interactions. This ongoing process of extinction and renewal underscores the delicate balance between destruction and creation in Earth's history. It serves as a testament to the adaptive capacity of life and its ability to find new pathways, even after profound disturbances. As we reflect on this, it becomes clear that mass extinctions, while tragic, are integral chapters in the story of life's enduring complexity. Considering how extinctions reshape ecosystems invites us to ponder the future of our own planet's biosphere. The patterns etched by past events offer insights into the resilience and vulnerability of life in the face of change. By understanding these ancient rhythms of loss and renewal, we gain a deeper appreciation for the intricate connections that sustain ecosystems and the evolutionary potential that lies beyond moments of crisis. With this perspective, we prepare to explore the specific ways in which new species emerge and evolve after mass extinctions, illuminating the pathways through which life continually reinvents itself. In the wake of mass extinctions, the natural world enters a profound phase known as the recovery period. This interval, often spanning millions of years, is characterized by both ecological upheaval and remarkable opportunity. As dominant species vanish, the ecological niches they once occupied become vacant, creating a canvas upon which life can innovate and diversify anew. During these times, ecosystems are fragile and dynamic, often undergoing repeated fluctuations as new communities establish themselves. Fossil records reveal that the pace of recovery varies depending on the severity of the extinction event and the environmental conditions that follow. Some ecosystems rebound relatively quickly, while others linger in a state of instability for extended durations. Yet, despite these challenges, life's tenacity becomes evident as new forms of flora and fauna emerge, gradually restoring complexity and balance. This resilient response highlights the adaptive potential of evolutionary processes, underscoring that extinction, while devastating, is not the end but rather a catalyst for transformation. The aftermath of mass extinctions unfolds as a delicate interplay between loss and renewal. With the fall of dominant groups, evolutionary pressures shift, opening pathways for previously marginalized or entirely new organisms to flourish. For instance, the Permian-Triassic extinction, the most severe event in Earth's history, eradicated over 90% of marine species and a significant proportion of terrestrial life. Yet, following this catastrophic loss, the subsequent recovery period witnessed the rise of modern vertebrate groups, including the ancestors of mammals and reptiles. Similarly, after the Cretaceous-Paleogene extinction, which ended the reign of dinosaurs, mammals diversified rapidly, filling ecological roles left vacant. This pattern illustrates how mass extinctions, while destructive, act as reset buttons that accelerate evolutionary innovation. The biological experiments conducted during recovery periods give rise to novel adaptations, morphologies, and interactions, ultimately reshaping the biosphere. Through this lens, extinction events are not simply chapters of despair, but also preambles to new evolutionary narratives. Studying these recovery phases deepens our understanding of nature's resilience and the intricate mechanisms that govern life's persistence and diversification. The fossil record, combined with modern genetic and ecological research, reveals that recovery is influenced by factors such as climate stability, availability of habitats, and the evolutionary histories of surviving lineages. During recovery, ecosystems often exhibit increased rates of speciation as organisms explore new adaptive zones. This burst of biological innovation can lead to the establishment of entirely new ecosystems, sometimes very different from those that existed before. For example, after the end Permian extinction, the prolonged recovery period saw the gradual replacement of ancient reef systems by new coral forms, signaling shifts in marine biodiversity and ecosystem structure. These transitions emphasize that recovery is not merely about returning to a prior state, but about forging new ecological equilibria. Such insights remind us that life's capacity to adapt is both profound and ongoing, continually shaping the diversity we observe today. The lessons embedded within recovery periods extend beyond paleontology, offering perspectives relevant to our current environmental challenges. The gradual rebound of ecosystems after past extinctions exemplifies the potential for life to endure and adapt, even in the face of significant adversity. However, the timescales involved also highlight the fragility of this process. Recovery is not instantaneous and can be impeded by ongoing environmental stressors. Understanding the tempo and mode of recovery helps illuminate the conditions necessary for biological renewal, emphasizing the importance of preserving ecosystem functions and genetic diversity. As we continue to witness rapid changes in the modern biosphere, reflecting on these ancient episodes of recovery encourages a mindful approach to stewardship, acknowledging both the resilience and limits of life on Earth. The study of these phases, therefore, becomes a bridge connecting past extinctions to future possibilities. In the wake of mass extinctions, ecosystems often find themselves stripped of many dominant species, leaving vast ecological niches unoccupied. These emptied niches create a unique opportunity for the survivors, organisms that managed to persist through the devastation, to diversify and explore new ways of life. This process, known as adaptive radiation, is marked by a rapid increase in the number and variety of species as they evolve to fill the ecological roles left vacant. Adaptive radiation is not merely a return to the status quo. It often results in the emergence of novel forms and functions, reshaping the biological landscape in profound ways. The extinction events reset the evolutionary stage, allowing lineages that were once minor players to rise in prominence, sometimes leading to entirely new ecosystems. This biological flourishing underscores the dynamic interplay between extinction and evolution, where loss paradoxically fuels innovation and diversification. The fossil record offers compelling examples of such evolutionary bursts following mass extinctions. After the Permian Triassic extinction, often called the Great Dying, the recovery period saw the rise of the dinosaurs, who capitalized on the vacant niches left by the disappearance of many reptilian and amphibian groups. Similarly, the Cretaceous-Paleogene extinction cleared the way for mammals to expand dramatically, eventually giving rise to the diverse array of species we see today. These periods of adaptive radiation are characterized by accelerated rates of speciation, as populations explore new ecological opportunities with reduced competition and predation pressures. The evolutionary experiments during these times can lead to the development of novel adaptations, such as new feeding strategies, locomotion methods, or reproductive behaviors, which contribute to the resilience and complexity of recovering ecosystems. It is important to recognize that adaptive radiation following extinctions is influenced by multiple factors, including environmental conditions, the availability of resources, and the genetic variability present within surviving populations. The evolutionary pathways taken during these times are shaped by chance as well as necessity, with some lineages thriving while others falter. Moreover, the pace of recovery and diversification can vary significantly between events, depending on the severity of extinction and the stability of the environment. Understanding these nuances enriches our appreciation of life's resilience and the intricate mechanisms that allow ecosystems to reorganize and flourish after profound disturbance. This perspective invites reflection on how contemporary biodiversity might respond to current and future challenges, bearing in mind the complex balance between destruction and renewal. With the demise of the non-avian dinosaurs approximately 66 million years ago, following the catastrophic event at the Cretaceous-Paleogene boundary, a profound shift unfolded in Earth's biological narrative. This mass extinction event eradicated a dominant group that had wronged terrestrial ecosystems for over 160 million years, effectively vacating numerous ecological niches. Mammals, which until then were relatively small and often nocturnal creatures living in the shadows of dinosaurs, found themselves presented with unprecedented opportunities. The sudden absence of large reptilian predators and herbivores opened pathways for mammals to explore new habitats and diversify in size, form, and diet. This remarkable episode of evolutionary expansion, known as adaptive radiation, was not instantaneous, but unfolded over millions of years, influenced by the prevailing environmental conditions and the genetic potential within mammalian lineages. As mammals expanded into these newly available roles, they began to occupy niches ranging from burrowers to tree dwellers, and eventually to large herbivores and carnivores. The ecological transformations set the stage for the emergence of species with more complex behaviors and physiological adaptations, laying foundational steps toward the eventual rise of primates, and much later, humans. This post-extinction era was marked by gradual but profound environmental changes, including shifts in climate, vegetation, and geography, all of which influenced how mammals evolved. Forests spread and diversified, providing shelter and food sources that supported a growing variety of mammalian species. The ability of mammals to regulate their body temperature internally, combined with more sophisticated brain structures, allowed them to thrive in these evolving ecosystems. This adaptability was crucial in an age where surviving life forms had to continuously adjust to fluctuating conditions. Over time, mammals developed a wide range of reproductive and social behaviors that further increased their chances of survival and success. The evolutionary narrative during this period underscores the delicate interplay between opportunity and adaptation, where the extinction of one dominant group catalyzed the rise of another. These complex dynamics illustrate how mass extinctions, while devastating, can act as resets that reconfigure the tree of life, enabling new forms to emerge and flourish in the aftermath. Among the diverse mammalian lineages that arose in the wake of the dinosaurs' extinction, the primates hold particular significance. Emerging around 55 million years ago, early primates began to exhibit traits such as enhanced vision, grasping hands, and increased brain size, adaptations that would prove essential for their survival in arboreal environments. These evolutionary developments set primates apart from other mammals, allowing them to exploit different resources and social structures. Over millions of years, primates diversified further, leading to the appearance of the hominid lineage that would ultimately culminate in Homo sapiens. The trajectory from tiny tree-dwelling creatures to intelligent beings capable of altering their environment is a testament to the intricate processes of natural selection and adaptation. It is humbling to consider that the rise of humans, with all their complexities, is rooted in this deep history of recovery and diversification following a mass extinction. In this light, the extinction of dinosaurs can be seen not only as an ending, but as a beginning, a pivotal moment that reshaped life on Earth in ways that continue to resonate today. The story of mammals rising after the dinosaurs also highlights the importance of resilience and flexibility in evolution. While mass extinctions often bring destruction, they also reset ecological boundaries, allowing surviving species to innovate and adapt in ways previously impossible. Mammals took advantage of these new conditions, experimenting with different forms and lifestyles that eventually led to the rich tapestry of species we observe now. This period after the dinosaurs' fall was not a simple or rapid recovery. Rather, it was a complex, branching process shaped by both opportunity and constraint. The fossil record reveals a mosaic of success and failure among early mammals, reminding us that evolution is not a predetermined path, but a series of contingent events influenced by chance and circumstance. Reflecting on this evolutionary chapter invites us to appreciate the delicate balance that governs life's continuity amid change. As we consider the rise of mammals following the extinction of dinosaurs, it becomes clear that such transitions are emblematic of life's enduring capacity for renewal. Each mass extinction has left an indelible mark on the planet's biodiversity, altering evolutionary trajectories and opening doors for new forms to emerge. The mammalian ascent after the Cretaceous-Paleogene event exemplifies how life can rebound, adapt, and ultimately transform. This ongoing process of extinction and recovery resonates through geological time, reminding us that the present diversity of life is the result of countless episodes of loss and regeneration. Looking ahead, these ancient patterns offer valuable insights into how current and future environmental changes may influence the living world. With this understanding, we can begin to explore the intricate relationships that define ecosystems and the evolutionary possibilities that lie beyond extinction. Fossil records stand as silent witnesses to the profound shifts in Earth's biological history, offering a window into the complex narratives of mass extinctions and subsequent recoveries. Through the careful study of these preserved remains, scientists have been able to piece together timelines that stretch back hundreds of millions of years, revealing when and how various species vanished. The fossilized bones, shells and imprints not only mark the disappearance of life forms, but also capture moments of ecological upheaval and transformation. These records trace patterns of sudden decline and gradual resurgence, illustrating that extinction is rarely an end, but rather a pivotal turning point. By examining layers of rock and sediment, paleontologists decode the subtle fingerprints of environmental change, such as fluctuations in climate, volcanic activity, and shifting ocean chemistry. Each fossil assemblage contributes critical data that enrich our understanding of the rhythms of extinction and survival. These insights emphasize that life on Earth is shaped by both fragility and resilience, as species repeatedly confront and overcome challenges across epochs. Within the fossil record, mass extinctions emerge as particularly dramatic chapters, intervals when a significant proportion of Earth's species abruptly disappeared. The Big Five mass extinctions, for example, have been studied extensively through fossil evidence, revealing how biodiversity was deeply reduced before slowly recovering over millions of years. These episodes often coincide with extraordinary environmental disruptions, such as asteroid impacts, intense volcanic eruptions, or rapid climate shifts. Fossils allow scientists to observe not only the timing of these extinctions, but also the aftermath, the patterns of ecological vacancy and rebirth. Following a mass extinction, ecosystems undergo a process of reorganization, where surviving species diversify and fill niches left open by the lost organisms. This adaptive radiation can lead to the emergence of entirely new groups and ecosystems, fundamentally altering the course of evolution. Fossil evidence highlights how recovery is not immediate, but a gradual unfolding, marked by innovation and experimentation in life forms. This cyclical dance of loss and renewal, preserved in stone and sediment, continues to inform our understanding of life's dynamic history. The study of fossils also illuminates the intricate interplay between extinction events and environmental conditions. By analyzing isotopic compositions and fossilized remains, scientists reconstruct ancient climates and habitats, providing context for why certain extinctions occurred. For instance, shifts in ocean temperature and chemistry are often reflected in marine fossils, revealing stresses that precipitated widespread die-offs. On land, changes in vegetation and atmospheric composition can be inferred from plant fossils and pollen records, which help explain terrestrial extinctions. These environmental reconstructions, paired with fossil data, allow for a more comprehensive understanding of extinction mechanisms and recovery pathways. Moreover, the fossil record shows that extinctions can act as evolutionary catalysts, removing dominant species and enabling others to flourish in new, adaptive landscapes. This reveals the profound interconnectedness between Earth's physical processes and the biological responses of life. Fossils, therefore, are not just remnants of the past, but key to unraveling the complex story of life's persistence through change. In the aftermath of mass extinctions, the fossil record captures the gradual re-emergence of biodiversity, often characterized by bursts of evolutionary innovation. New groups arise, filling ecological niches that were once occupied by extinct species, leading to novel forms and behaviors. This process of recovery can span millions of years, as life adapts to altered environmental conditions and ecosystems stabilize. Fossilized evidence of transitional species provides glimpses into evolutionary experimentation, where traits are tested and refined through natural selection. Such periods of evolutionary radiation highlight the creative power inherent in life's capacity to rebound from catastrophic loss. The patterns observed in fossils suggest that extinction events, while devastating, also reset ecological dynamics, triggering waves of diversification that shape the trajectory of life on Earth. Through these cycles, the fossil record continues to offer profound lessons about resilience and transformation in the face of adversity. As we delve deeper into the fossil archives, we gain not only a clearer picture of past extinctions, but also a framework for anticipating future biological responses to environmental change. The rhythms recorded in stone remind us that while extinctions are natural components of Earth's history, the pace and scale of current biodiversity loss may differ from ancient events. Fossils teach us about thresholds, recovery times, and the delicate balance within ecosystems. They encourage a thoughtful reflection on humanity's role in shaping the planet's biological future. By appreciating the wealth of information preserved in fossils, we prepare to better understand the evolving relationships among species and environments. This knowledge sets the stage for exploring how contemporary ecosystems may transform and adapt in the face of ongoing change. From these ancient records, the story of life's enduring dance with extinction and renewal continues to unfold. The history of mass extinctions is etched deeply within Earth's geological record, revealing episodes when life's diversity was dramatically curtailed by sudden and widespread environmental upheavals. These moments, occurring over millions of years, saw the disappearance of vast numbers of species, altering the course of evolution and reshaping ecosystems on a global scale. Yet, following each great extinction, life exhibited remarkable resilience, gradually recovering through complex processes of adaptation and speciation. This cyclical pattern of loss and renewal underscores the dynamic nature of biodiversity, where extinction serves as both an end and a beginning. However, the intervals between these ancient events were often measured in millions of years, allowing ecosystems sufficient time to stabilize and regenerate. Today we face a different scenario, one where the pace of species loss accelerates amid unprecedented environmental pressures. Understanding the magnitude and consequences of past extinctions provides a crucial lens through which we can examine and respond to the vulnerabilities of modern biodiversity. This perspective invites a deeper appreciation for the delicate thresholds that maintain ecological balance and the potential consequences when these thresholds are crossed. In the aftermath of mass extinctions, ecosystems undergo a prolonged period of transformation, where vacant niches invite evolutionary innovation and new forms of life emerge to fill the void. These recovery phases, often spanning millions of years, highlight nature's capacity for renewal, characterized by shifts in dominant species and altered food web structures. Fossil evidence reveals that following the Permian extinction, for example, ecosystems gradually transitioned from simple assemblages to more complex communities, setting the stage for the rise of dinosaurs and eventually mammals. Such recoveries illustrate the interconnectedness of life and the importance of biodiversity in sustaining ecosystem functions. Today, however, the rapid loss of species threatens to disrupt these connections before they can be restored, limiting the resilience inherent in natural systems. By studying how life rebounded after past crises, scientists gain insights into the mechanisms that support recovery and the timescales necessary for ecosystems to regain stability. This knowledge is instrumental in guiding conservation strategies aimed at preserving biodiversity, enhancing habitat connectivity, and promoting ecosystem resilience amidst ongoing environmental change. It reminds us that while nature's capacity to recover is profound, it is not infinite, nor is it guaranteed under current rates of disturbance. The modern era, often described as the Anthropocene, is marked by human influences that accelerate extinction risks beyond those recorded in ancient times. Habitat destruction, climate change, pollution, and invasive species create a mosaic of challenges that compound the pressures on global biodiversity. Unlike past mass extinctions driven by natural cataclysms, today's biodiversity crisis is predominantly shaped by the cumulative impacts of human activity. This unprecedented context calls for a nuanced understanding of extinction dynamics, informed by paleontological and ecological research. By integrating lessons from deep time with contemporary observations, scientists and policymakers can better anticipate potential tipping points and develop adaptive management approaches. These efforts aim to mitigate further losses by fostering sustainable interactions between human societies and the natural world. In this way, the echoes of past extinctions resonate within current conservation initiatives, emphasizing the urgency of stewardship and the potential for proactive intervention. It is through this synthesis of historical insight and modern science that we may chart a course towards safeguarding the rich tapestry of life on Earth. Importantly, the study of past extinctions also reveals that recovery and renewal often depend on the preservation of genetic diversity and ecosystem complexity. The remnants of life that survive initial extinction pulses serve as the foundation for future evolutionary trajectories. Protecting existing biodiversity is therefore not merely an act of preservation, but an investment in the resilience and adaptability of life as a whole. Current conservation efforts increasingly emphasize the protection of keystone species and critical habitats, recognizing their role in maintaining ecological networks. Additionally, restoration ecology seeks to rehabilitate degraded environments, fostering conditions conducive to natural regeneration. These approaches reflect an understanding that the health of modern ecosystems is inextricably linked to the lessons gleaned from Earth's deep past. Such perspectives encourage a long-term view, one that appreciates both the fragility and persistence of life amid changing conditions. In this light, the challenges we face today are part of an ongoing narrative where informed action can influence the unfolding chapters of biodiversity's story. As we continue to explore the intricate dance between extinction and renewal, it becomes clear that the future of biodiversity is not predetermined, but shaped by choices made in the present. The fossil record offers a mirror reflecting the consequences of environmental shifts, while also illuminating pathways toward recovery. With this knowledge, humanity holds a unique position as both a driver of change and a potential guardian of life's diversity. The integration of paleontological wisdom and modern ecological science fosters a deeper understanding of the mechanisms underlying extinction risks and recovery potential. This foundation supports efforts to develop innovative conservation strategies, promote sustainable resource use, and engage communities in stewardship. In embracing this role, we acknowledge the profound interconnectedness of all species and the shared responsibility to nurture the living world. From the shadows of ancient extinctions, new hope emerges, guiding us into the ongoing journey of biodiversity's enduring transformation. Throughout Earth's deep history, life has endured 5 major mass extinction events, each marked by the rapid loss of vast numbers of species. These profound biological crises, triggered by factors such as volcanic eruptions, asteroid impacts, and dramatic climate shifts, have reshaped ecosystems and paved the way for new evolutionary chapters. In the aftermath of these extinctions, nature has demonstrated an extraordinary capacity for recovery and diversification, often over millions of years. Yet, today, scientists observe patterns of species decline and habitat degradation occurring at an unprecedented pace, raising questions about whether we stand on the brink of a 6th mass extinction, one driven not by natural catastrophes, but by human activity. This emerging debate centers on the scale and speed of biodiversity loss in the context of global changes instigated by humanity's expansion and resource use. The recognition of this potential new extinction event brings with it a sober understanding of our role as both contributors to and potential mitigators of ecological collapse. The ongoing discussion among ecologists, paleontologists, and conservationists highlights the complex interplay between human influence and natural processes. Unlike ancient extinctions, which unfolded over thousands to millions of years, the current rates of species loss are measured in decades and centuries, timeframes that challenge the resilience of ecosystems. Habitat destruction, climate change, pollution, and the introduction of invasive species all contribute to this accelerated decline. Yet the question remains, does this rapid turnover qualify as a mass extinction comparable to those recorded in the fossil record? Some researchers argue that the sheer velocity and breadth of loss fulfill the criteria, while others urge caution, emphasizing the need for long-term data and nuanced interpretation. This scientific conversation underscores the importance of understanding extinction not just as an endpoint, but as part of a dynamic evolutionary process influenced by multiple factors. In this light, the debate itself becomes a catalyst for deeper inquiry and reflection on our responsibilities. Beyond the academic discourse, the implications of the sixth extinction debate resonate deeply with conservation efforts worldwide. Recognizing human activity as a principal driver compels a shift in how societies value and interact with the natural world. Conservation strategies now increasingly focus on preserving genetic diversity, protecting critical habitats, and restoring ecological functions that support resilience. These efforts are informed by lessons drawn from past extinction events, how ecosystems have collapsed and eventually rebounded. By integrating historical context with modern science, conservationists aim to foster environments where species can adapt and thrive amidst changing conditions. Furthermore, this approach embraces a holistic perspective, acknowledging the interdependence of species and the ecosystems they inhabit. The urgency conveyed by this debate encourages collaborative action that transcends borders and disciplines, fostering hope amid uncertainty. As the conversation continues to unfold, it also invites reflection on humanity's place within the biosphere and the ethical dimensions of biodiversity loss. The potential onset of a sixth mass extinction challenges us to consider how our choices ripple through time, affecting not only present-day species, but future generations as well. It is a reminder that extinction is a permanent removal from the tapestry of life, one that diminishes the richness of the natural world. Yet, the very awareness of this possibility imbues us with agency, the capacity to intervene, to protect, and to restore. Scientific understanding combined with cultural and policy initiatives can shape pathways toward coexistence and regeneration. This ongoing dialogue thus becomes a space where knowledge meets responsibility, inspiring a collective commitment to stewardship. In this way, the sixth extinction debate is not merely a scientific issue, but a profound call to mindfulness and care. From this vantage point, the study of mass extinctions and their aftermath continues to reveal the remarkable resilience and adaptability of life on Earth. Recovery from past extinctions involved complex processes of ecological reorganization, evolutionary innovation, and geographic redistribution of species. These patterns offer valuable insights into how ecosystems might respond to contemporary pressures, emphasizing both the fragility and tenacity inherent in living systems. As scientists deepen their investigation into the current biodiversity crisis, they also explore ways to enhance natural recovery through conservation biology, habitat connectivity, and sustainable management. The dialogue between past and present extinction events enriches our understanding and informs hopeful strategies aimed at sustaining biodiversity for the long term. This evolving narrative invites us to remain attentive to the delicate balance between loss and renewal as it unfolds in our time. When mass extinctions sweep across the Earth, they do more than erase vast numbers of species. They fundamentally reshape the structure of ecosystems. In the wake of such profound loss, the remaining organisms find themselves in a world with altered environmental conditions, new opportunities, and vacant ecological niches. This reset initiates a process of ecosystem shifts, where the balance of interactions between species and their habitats changes, often dramatically. Early successional species, typically fast-growing and adaptable, can dominate these newly opened landscapes, setting the stage for a gradual rebuilding of complexity. Over time, new food webs emerge, and fresh evolutionary paths are explored. This reorganization is not a simple return to what was lost, but a transformation that reflects the altered planet. The study of these post-extinction ecosystems reveals how life's resilience is woven through adaptation and innovation, illustrating the dynamic interplay between survival and change. Following a mass extinction, the ecosystems that develop tend to exhibit novel combinations of species and functions. The disappearance of dominant groups allows previously minor or suppressed lineages to flourish, often leading to rapid diversification and the appearance of new ecological roles. For example, after the Permian-Triassic extinction, the most severe in Earth's history, the recovery saw the rise of archosaurs, ancestors to dinosaurs, which would later define entire terrestrial ecosystems. Similarly, marine ecosystems underwent profound shifts as new groups of invertebrates and vertebrates expanded to fill emptied niches. These patterns demonstrate that extinction acts as both an end and a beginning, a boundary between ecological chapters. The slow but steady establishment of complexity after such upheaval showcases nature's capacity for innovation and the continuous dance of life, adapting to changing conditions. These insights emerge from fossil records, comparative biology, and ecological modeling, helping us understand the tempos and modes of ecological recovery. The recovery of ecosystems after mass extinctions is often uneven and regionally varied, influenced by factors such as climate shifts, geographic isolation, and the availability of resources. Some environments may recover quickly, while others remain depauperate for millions of years. This patchwork process creates a mosaic of biological communities in various stages of succession and diversification. Such variation highlights the complexity of ecological dynamics and the importance of local conditions in shaping the trajectory of life's rebound. Moreover, these ecosystem shifts can influence the course of evolution itself, as species adapt to novel associations and selective pressures. The emergence of new dominant groups frequently coincides with innovations in physiology, behavior, or reproductive strategies, underscoring the intimate link between ecological context and evolutionary potential. By examining these processes, scientists gain a deeper appreciation for the intricate feedbacks that govern life's renewal after profound disturbance. Understanding what happens after mass extinctions is crucial not only for reconstructing Earth's deep past, but also for informing our approach to present and future biodiversity challenges. The lessons embedded in ancient ecosystem shifts remind us that recovery is possible, though often slow and contingent on multiple interacting factors. They also caution us about the fragility of ecosystems facing rapid environmental changes and the importance of maintaining connectivity and diversity to support resilience. As conservation efforts strive to mitigate human impacts, the parallels between past and current extinctions underscore the urgency of fostering conditions that enable natural recovery processes. This perspective enriches the dialogue between paleontology, ecology, and environmental science, offering a holistic view of life's enduring capacity to reorganize and adapt. These reflections guide us toward a mindful stewardship of the natural world as it continues to evolve amid ongoing challenges.